Hello, my name is Amin Ranem, and I'm happy to introduce you our work on continual atlas-based segmentation of prostate MRI. So first of all, why do we need continual learning in medical imaging? Hospitals are dynamic environments, which means that populations change over time, devices and acquisition practices and protocols also change over time, and therefore lead to domain shifts within the data. Now, having such shifts in the data harms our model's performance. That's of course something we want to prevent. Additionally, we have patient privacy regulations within hospitals that prohibits us the storage of patient data. So a traditional static learning approach where we have multiple data sets and can train on them simultaneously does not work anymore. Now we have to train continuous on a sequence of data sets that we get over a specific time. Now the goal of continual learning is basically the more data I use for training over time, the better I should become across all seen tasks. Now in reality, what we observe is when we train on a specific task and we evaluate on the test set of this task, we perform pretty good in general. However, when we then want to apply this model on an unseen data set, we see a performance drop, which is known as plasticity loss and is a lack of generalizability. Now we can say, okay, we train on this second new data set and redo the testing. And what we see there is that the performance on the new data set is indeed increased. However, the performance on the previous, in this case, green data set is reduced, which is known as catastrophic forgetting. And that's of course something we want to mitigate in a continuous setup or in continual learning setup, because we actually want a positive backward transfer, which means that we want to maintain our knowledge that we acquired already and also learn new information. And we also want to perform pretty good on unseen data sets, even though we haven't trained on them, which is known as forward transfer. When we now look at the continual learning methods that exist, the most promising one is the rehearsal method, which just stores samples from each dataset and interleaves them for later stages. We also have sparse connectivity or regularization-based methods, and even expansion-based methods like networks that expand specific layers when new tasks are introduced, or we have multiple models. For every task we have one model, or we have a shared body and multiple heads. When we now look at the challenges that come with continual learning methods, we already said that rehearsal is a very promising method. However, we cannot really use this for medical imaging as we have to store patient information, which is not allowed. When we look at regularization or distillation methods, we always deal with a rigidity or plasticity trade-off which comes with the hyperparameter tuning. If my network is too rigid, this basically means I maintain knowledge, but I'm not able to acquire new knowledge, whereas plasticity means that I can acquire new knowledge, however, I forget a lot of previous knowledge. And both cases lead to segmentation masks which are not coherent anymore and cannot be used. The other group, the third group, expansion or sparsity-based method, they are dependent on capacity because, of course, the more data sets I train on, the larger my networks get, which at a certain point might not be feasible anymore. So as a next step, we wanted to compare traditional segmentation using UNet and atlas-based segmentation, and we observed that the performance for end-to-end segmentation actually is dependent on the task that has been used for training. So when we train on the first task and evaluate on all 7 tasks, we get a better performance for a unit as when we would train on the 5th task and evaluate across all tasks. However, for atlas-based segmentation, we achieve a stable performance, robust results, and a proper generalizability. And with this knowledge, we then want to use atlas-based segmentation, and we have to deal with the question, how do we get a registration done if we only have one input image and expect a segmentation mask as an output? Therefore, we used 4 different prototypes based on the endorectal coil that is normally used during acquisition. Now, this is a acquisition practice that changed over time, as nowadays endorectal coils are not used anymore, and therefore we have 4 groups. We have 1 prototype which represents images acquired without an endorectal coil, and 3 that represent images that were acquired with endorectal coils based on the visual appearance of being dark coil, a bright coil, or something in between. Now, when it comes to the prototype generation process, Let's say we have a data set which was acquired without endorectal coil and we want to generate a prototype out of this. What we then actually do is select a set of images, let's say 7 images. We perform a rigid alignment between those images and take the average. Taking the average of those rigidly aligned images is a first step to privacy preservation, as we don't just store the actual samples to a hard disk and interleave them later on. And of course the same is applying to segmentation masks, in order to have a prototype image and a corresponding segmentation mask that can be used for registration and generating segmentation. Now, to determine the privacy of our prototypes, we performed a user study where we had 2 participants, 2 groups of participants. We had radiologists and we had computer scientists. And during the study, all prototypes were presented in specific blocks, and every block contained a prototype and 3 samples. And from those 3 samples, only 1 sample was used to generate this prototype. And looking at the results, we see that neither one of those groups even hit the 50% precision mark, which indicates that, at least from a human perspective, it's privacy preserved enough to not be able to correctly distinguish between patients that were used to generate the prototypes and patients that were not even used to generate those prototypes. Another important thing is the inter-prototype performance. By performing such an ablation study, we came to the conclusion that the choice of the prototype one uses during inference plays a significant role on the performance. And that's kind of obvious. I mean, if you have an image that uses an endorectal coil, you would not use the prototype which represents a acquired image with no endorectal coil. So how does our process differ from traditional end-to-end continual learning? Let's say we have a sequential setup, which is just a transfer learning of different models. So you have a model which is trained on different data sets, and when data sets arrive, we just perform transfer learning. Then we have rehearsal, which is a promising method, but again, it interleaves samples and stores them, which is not privacy preserving. And our Atlas replay uses Atlas-based segmentation based on our generated prototypes, which maintains structural information and domain information that helps to maintain knowledge over time. When we then look at the results, we see that sequential is obviously not performing good in maintaining knowledge nor generalizing well. Looking at the regularization-based methods, they play in the same ballpark, except the incremental learning technique. When we look at the spider plots, they basically just indicate the performance of the final model trained on all 7 stages evaluated across all 7 tasks, and the larger the area, of course, the better the method. And Riemannian walk even performs worse than simple sequential. When we now look at the rehearsal-based methods, we see a significant difference for the traditional rehearsal and the Bayesian correction. They have a very, very low backward transfer, so they maintain proper knowledge. However, the forward transfer is not really that significantly increased, so they still don't generalize that much. In Atlas, our Atlas replay method, on the other hand, achieves same backward transfer performances as rehearsal and a superior forward transfer. And we will see this right now in this quantitative analysis, where we had a ground truth image which was extracted from the test set of the 3rd data set. And after every intermediate stage of training, we performed inference on this image and then plotted the segmentation mask. And we see for sequential and elastic weight consolidation before the stage 3, so before training on the distribution of this data, we're not even able to actually predict the shape of the prostate. After trained on the 3rd task, we know how the prostate looks like. However, the more we train on additional tasks, the worse it gets, which indicates the catastrophic forgetting. For Atlas replay, since we have the prototype with the corresponding prostate segmentation, we already have structural information that can be used, and we just have to shift the voxels or pixels of the segmentation mask in such a way that they align with the actual image we want to segment. And there we see we have a way better forward transfer and, of course, a mitigated catastrophic forgetting. So thank you very much for listening, and if you have any further questions, you can reach out via LinkedIn, Twitter, or email, or we can discuss more during the poster sessions.